In our last subject in nuclear chemistry, we're going to talk about applications of some of this nuclear stuff we've been talking about. Now, one of the most common applications of nuclear reactions is for medical purposes. And I mentioned in a previous video a thyroid scan, which is iodine-131 undergoing beta decay. And it turns out the thyroid preferentially absorbs iodine. And if you have hyperthyroidism, you're going to absorb a lot of iodine. If you have hypothyroidism, you're not going to absorb much. And so they give you this cocktail that contains iodine-131, and they look at how much iodine-131 your thyroid is absorbing. And how they look at that is they're actually looking at the beta particles that are coming off of your thyroid. So as your thyroid ingests that iodine-131, it's going to have more beta particles coming off of it because it's got this radioactive iodine in it. And this is an image that this little device down here is acquiring from the thyroid that says, hey, this is about how much radioactivity is coming off of different parts of the thyroid. And someone who knows what they're doing, and I am not one of those people, can look at this image and decide, oh, that's more iodine-131 than we expect, or that's less iodine-131 than we expect. But let's go ahead real quick and figure out what iodine-131, when it decays in your body, leaves behind. So we've got iodine-131. We look over on the periodic table. Iodine is element number 53. It's undergoing beta decay, if you remember, is 0 minus 1. And so balancing mass number and atomic number, the thing that's left inside your body is xenon-131, which is a harmless, noble gas. And so, yes, there's some radiation in your body, but at least the thing that it leaves behind is pretty harmless. Another application is if you've ever heard of a PET scan. It stands for Positron Emission Tomography. Well, if you remember what a positron is, it was that positively charged electron, the antimatter. I don't know if remember if I used that term, but that's antimatter. It's matter with opposite charges. And it exists. It's kind of weird, but it does. And so what they do is they get some fluorine-18, which undergoes positron emission, and they put it where they're looking for cancer in general, is what PET scans are used for. And in fact, brain cancer is one of the most common ones. Now, if you remember from your biology or physiology classes, it's really difficult to get chemicals into the brain. There's a blood-brain barrier. There's all sorts of protections for your brain. So what they do is they attach this fluorine-18 to sugar molecules. And the brain loves sugar molecules. And in fact, cancer is just unregulated cell growth. So cells that are growing really need a lot of sugar. So the cancer cells inside a brain are going to be absorbing a lot more of that sugar and a lot more of the fluorine-18 and are going to become a little bit more radioactive. And what they're going to do is they're going to have a device that looks for that positron emission and make these little images that look like this. Now, I have no idea how to interpret this image as to what's normal and what's not, but someone who's experienced in the field obviously does and can look and be like, hey, there's a lot of activity in this part of the brain and maybe there shouldn't be, and so they can start to detect the signs of cancer in the brain using positron emission tomography. So what's left in your body after that fluorine-18 decays into it's positron. What's a positron? 0 plus 1e. And then what's left behind is 18 and 8. And what's 8 is oxygen. So that fluorine just turns into an oxygen atom, and which isn't a bad thing to have in your body. So that is how PET scans work. And a lot of people wonder about CAT scans. Well, CAT scans aren't directly using any sort of radioactive decay, but they are using X-rays. And so it's actually high energy light that's coming at you. It's not actual particles that like the beta decay and the positron decay that we just talked about in the iodine and in a PET scan. Now, an interesting thing about CAT scans is it's a very large exposure. One doctor once told me, and I haven't double checked it, but it's about the equivalent of 100 chest X-rays. So very, very large radiation exposure. Now, I've had some experience in the past where my children have needed to get a CAT scan, and it's hard as a parent to look and say, hey, yes, they need this high radiation exposure, especially because MRIs, anybody know how much radiation exposure you get from an MRI? It's none. It's no radiation exposure whatsoever. It's high-powered magnets, but no radiation, no X-rays, no positrons, no beta particles, anything like that. And so an MRI can tell you almost everything a CAT scan can, But there's two things going for a CAT scan. One is it's a lot faster, and two is it's a lot cheaper. And so CAT scans are still used very regularly and routinely, even though they're high radiation exposure, due to those two things, is speed and cost. Now, I wish it wasn't the case. I hope that in the future MRIs get better and better, and they can replace the CAT scan with MRIs, but that's what they have right now. We also use radiation as therapy. We don't just use it to diagnose things, we use it to treat things. And what I want you to do is look at this chart here, which talks about radiation exposure for diagnostic and therapeutic reasons. So if you're trying to diagnose a liver cancer, you might expose someone to 0.3 rems of radiation. And if you remember from this table over here, the LD50, lethal dose in 50% of the population for a human, is 500 rems. So liver diagnosis, very, very low radiation exposure comparatively. That's about 300 millirems. And if you remember, the ground gives you about 30. So, this is 10 times what you get in a year just from the ground. Okay. Now, if you go down to a thyroid scan, that's 50. Well, that's a tenth of the lethal dose. So it's like pretty significant radiation exposure just for a diagnostic test. But in many cases, that exposure gives so useful information that the risk of the exposure is worth it to get a correct diagnosis that can then be taken care of. But what I want you to pay attention to down here is what happens when we treat cancer. You should be looking at these numbers and thinking 4,500 is a whole lot more than 500. So if we're treating lymphoma or skin cancer or lung cancer or brain tumors, shouldn't every one of those patients be dying from the radiation exposure that they're getting? And the answer would be yes, if it was exposed to the entire body. However, each one of these therapeutic things is very, very focused. And so if you're trying to treat skin cancer, you've got very focused radiation exposure on that skin cancer, enough to pretty much kill everything that radiation is exposed to. And so you're killing all the skin cancer, you're also killing all the regular cells, which is why there's a lot of side effects from radiation therapies. But it's enough to get rid of those cancerous cells. The one that's not on here is one that does expose your entire body to radiation, and that's chemotherapy. And I looked it up once, that chemotherapy gives you about 800 rems of radiation exposure. I don't have a reference for that, so if you're going to make some arguments with people, you should go look it up yourself just to be sure. But it's about 800 rems. 800 is a bit more than 500. And so again, you'd think chemotherapy, a lot of these patients should be dying. But what happens in chemotherapy is, yes, it's exposing your entire body to a huge amount of radiation, but it's over time. And so it's careful application of that radiation over time is enough to treat the cancer cells, because they're very active, very vigorous, and so they're more likely to be damaged by that radiation, versus your regular cells, which are a little more calm and less likely to be affected by that radiation. But it is a very significant thing, which is why there's so many side effects to chemotherapy, is because essentially you are exposing yourself to an almost lethal dose of radiation. But done well, it can actually save someone's life. And I know people who have been cured of cancer from their chemotherapy treatments, and so it can be a very, very good thing. Two other ways that we use nuclear energy is nuclear fission and nuclear fusion, one of which we're very good at and one of which we're not so good at. We're going to talk about nuclear fission first, and that's power plants. So if you've ever driven by a nuclear power plant, here's one right by an ocean, here's one that's not by an ocean, and I can tell the difference between the two because how a nuclear power plant works. It's the funniest thing in the world, really. So a nuclear power plant, it has nuclear reactions in it. And if you remember, I told you that these nuclear reactions, these falling apart of molecules, or these, what we're going to see later is combining of molecules, releases a ton of energy. Not molecules, atoms, sorry. Releases a ton of energy, ridiculous amounts of energy. And we can harness that energy and put it out in electrical wires. That's what the point of most electrical power plants is to convert to electrical energy. Now, it turns out it's not very straightforward to just turn energy, which usually comes in the form of gamma rays or heat, into electrical energy. And so what do? We take these nuclear power plants, it's got these highly radioactive materials in them, and we're generating a lot of energy. And we use it to boil water. Why do we boil water? I mean, we're harnessing the power of the atom, and we're boiling water. Well, it turns out when you boil water, you make steam. Steam is great for turning turbines. Those turbines generate electricity, which is then put out into the electrical grid. So if you're boiling water, well, if you want to do it again, you either need new water, which you don't really want to use that much water, or you need your water to cool down again. And so this one here, which is from The Simpsons, yes, those cooling towers are actually, the only purpose is the water runs through them, and it allows the water to cool back down so it can be run through the system again, reboiled to turn those turbines. You don't see these giant cooling towers on power plants that are near large water sources, because what they have is underneath these water sources, they have these giant closed pipes that just put the hot water out through the pipe, bring the cold water back in from the pipe. It's not changing water with the ocean or anything like that. It's just using the cold ocean to cool down the water that's in those pipes. And so that's why you don't see those cooling towers at power plants that are near water sources. All right, so that is what essentially nuclear fission plants are doing. And all the nuclear power plants that we have in the world right now are nuclear fission plants. And fission, let's define these terms. Fission is breaking apart atoms. And we'll see an example of that in the next slide about what this reaction looks like. Fusion, just like fusion cuisine, if you're eating, is combining of things. It's combining atoms. So you're slamming two atoms together to make a new atom. So, oops, those two. Our fission reactions, how do they work? Well, most commonly, uranium-235 is what's present inside a fission nuclear reactor. So pretty much every nuclear reactor that's out there that's generating electricity has uranium-235 in it. When a neutron, high-energy neutron, hits uranium-235, it makes uranium-236, which is very unstable and decays almost instantaneously into krypton-91, barium-142, 3 neutrons, and a whole lot of energy. Lots and lots and lots and lots and lots of energy. Now, how does this reaction do anything? Well, it turns out that each of these neutrons can then start another reaction by hitting another uranium-236. So each of these neutrons can make 3 more neutrons. And then each of those neutrons can make 3 more neutrons. And each of those neutrons can make 3 more neutrons. And all of a sudden, if you've ever heard of a chain reaction, this is a chain reaction. This is one thing can make 3 things, those 3 things can make 9 things, those 9 things can make 27 things, and you have this exponentially increasing thing. And if you're not careful, this whole thing goes kaboom. So how do they prevent it from going kaboom? Is in most nuclear power plants, they have a way of absorbing extra neutrons and making sure that some of these neutrons are neutralized so they don't make that next branch. Right? And if you're very careful about that, then you can only have as much as you want and not so much that it goes boom. And when nuclear power plants melt down, it's often because that safety mechanism has some sort of trouble with it. Now, I'm going to also mention very quickly, barium-142, krypton-91, those are also radioactive. They also decay into other things. And these radioactive decay processes from nuclear fission are some of the nastiest chemicals on the face of the Earth. Horrible chemicals. In fact, we don't even understand the chemistry of a lot of them. And to make even worse is their half-lives are hundreds of thousands of years. These things are going to be around for a long, long, long time. So nuclear fission makes a whole lot of waste that's really, really awful. And so it's not a good process to be doing in the long term. However, it generates a ridiculous amount of energy compared to its waste. So if you compare the waste in a nuclear reactor to the waste of a coal burning or even a natural gas burning power plant, it's minuscule. It's very, very small in terms of quantity, but the nastiness of it is significantly higher. So there's always trade-offs in whatever different ways we want to generate electricity other than renewable resources. But even renewable resources, we have to build all the things to harness those renewable resources. And building things like batteries, building things like solar panels, is actually also creates a whole lot of nasty chemical waste. So there's no great, perfect answer to clean energy yet. Now, unfortunately, one of the other things that people use nuclear energy for is to create nuclear bombs. And what a nuclear bomb does is it takes advantage of that chain reaction. It says that the 3 makes the 9 makes the 27, and that happens extraordinarily quickly. And if you do it well enough, all that energy comes out essentially instantaneously, and you get a very, very large explosion. You remember, if you've ever heard, people generally measure the size of a nuclear bomb by megatons of TNT. Millions of tons of TNT. So imagine you had just this dynamite filling up entire giant, huge buildings, and that's what we mean by megatons of TNT. Huge, huge buildings filled up with TNT, and that's the energy in one nuclear bomb that might fit into a suitcase. Crazy amount of energy in these things. I'm not going to go into the detail too much of how they work, but it is very interesting because you want a nuclear bomb to be stable if it's just sitting on a shelf, right? You don't want it to spontaneously explode, but you want to be able to make it explode whenever you want it to. And what they do is they have a lump of radioactive material that's just big enough that it's not going to ever explode on its own. It's got enough nuclear material that it's kind of warm and fuzzy in there, but most of the neutrons are escaping and they aren't hitting the other ones and causing this kind of long chain reaction. However, if you do things just right and you explode inside a very, very well-sealed container, if you explode something, it makes this huge pressure wave that can actually compress the solid that is your nuclear material. And when it compresses, there's now atoms close enough to each other that that chain reaction can happen, and that's how you get that boom. That's how you get that sudden release of energy, by compressing that thing enough very, very suddenly so that it's now this little tiny ball where that chain reaction can happen. And that's essentially how most nuclear bombs work. Now, wouldn't it be great if there was a way of making energy where there was essentially no waste? Where you could produce a lot of energy with no waste. And that's what people have been looking for years. And a lot of those renewable resources that we have, they're great, but they do produce their own waste. I mean, you want to make a hydroelectric dam, the concrete production is a horrible thing, and concrete releases a huge amount of CO2 in the atmosphere. So there always are trade-offs. But it turns out there's this thing called nuclear fusion. And nuclear fusion is an amazing concept. You take two forms of hydrogen. You take hydrogen with 2 neutrons, and you take hydrogen with 1 neutron, and you combine them together, and you make helium, another neutron, and ridiculously more energy than a nuclear fission power plant does. Now, these two forms of hydrogen, this one is present in the ocean. You can just get it from the ocean. It's just present in water. This one we do have to make, but we know how to make it, and you don't need a whole lot of it. And what's amazing about this one is if you think of this particular one, how much of that do we need? Well, in order to power the world's energy needs, I mean the entire world's energy needs, you'd only need about as much seawater and extract all the what's called deuterium, the hydrogen with 1 neutron, extract the deuterium from the seawater that fits in a 2-story office building. And that would be enough deuterium to supply the world's energy needs. Now, what are the products of this? The products of nuclear fission were these horrible things that were also radioactive and had half-lives of hundreds of thousands of years. But the only byproduct of this reaction is helium and a neutron. Neutrons are easy. We can absorb neutrons. That's not a problem. And helium, well, I mean, that's your helium balloon right there, right? The only side effect of this is, if you were to breathe it too much, well, your voice might sound like this, and then you wouldn't have to worry about it. So we have this way of making lots and lots and lots of energy with essentially no byproducts, no problem. So why don't we do this? Well, the answer is because in order to get this reaction started, you need a temperature of about 100 million degrees Celsius. And that's a little hard to do. because that's the temperature of a sun. That's the temperature of a star, because this is one of the reactions that's happening primarily in stars, is the combination to make helium. So you need a temperature of 100 million degrees Celsius. That's not easy to do. And then you need to sustain it and do it over and over and over again if you want it to be a power source that's stable for the world. We've been working on this concept for a long, long time. And we're making progress, but it's slow progress. Billions and billions and billions and billions and billions of dollars have been spent for very, very slow, very, very minimal progress. And some people wonder, is it worth it? Is it really worth it to be spending all of this money on these projects that aren't producing things very, very quickly? And it's a hard question. It's not an easy question. But the payoff of this one, if we can get it to work, is so amazing that we could solve the world's energy needs in a completely clean, no waste kind of way with very small amounts of material, that if we can get it to work, it's so worth it. But there's also a chance it'll never work. And that's the thing about science, is you never know if something's going to work. But you try and try and try until you either prove that you can or prove that you can't. So that is our foray into nuclear chemistry. I hope you found it interesting. There's all sorts of very interesting things that happen in nuclear chemistry. And thanks for listening.